Hello, good morning. So welcome to the next section. So in the last class, so today we are going to discuss about what is called as the IPv format. So already in the previous class we have discussed the IPv format. So today will be just briefly we are going to walk through this IPv format and fragmentation. So now when we are talking about the IPv format or the datagram header, so already we said that so IP datagram header, now it consists of header and the data, right? Now we can say this is what the header looks like of our IP datagram. Now here, so header takes minimum 20 bytes. So 20 to 60 byte is of header and the remaining is the payload, the actual payload. So we have seen that what will be the actual payload. So payload will be from 0 to 65,515. So 0 to 65,515. So this will be the actual the payload. So payload will be this much and the header of our IP datagram will be minimum 20 bytes, right? Now also, now if you look here, so now this is what the IP header format looks like. So we have got the version which is a 4-bit, now header length of 4-bit, type of service, so we call it as TOC or DSCP. So the DSCP or type of service is of 8-bit and the total length is 16-bit. The second layer, now we told that it is completely related to our fragmentation, so which we are going to discuss in today's class. So where we have the identification bits, flag bit and the fragmentation offset. Then we have TOL, that is the time to live, TTL, that is time to live, protocol is of 8-bit, and we have got header checksum which is of 16-bit information. Then source IP address, now the source IP address will be of 32 bits. The source IP address is 32-bit. Similarly, destination address is of 32 bits. So now when you count all these bits, now the total you are going to get is 2 raised to the power of 16 minus 1. So or we can say 65,535. So why we are telling 65,535 the total? Because so we have this data is of 65,515 plus you are going to add the header size. So the header is of how much? Minimum is 20 bytes. If you add, so we get 65,535 bits is the complete IP datagram. Now if we talk about the version, so we discussed the first field of our IP protocol or the packet is called as the version. So now this value, that is the version which is a 4-bit value, since we are using the IP version 4, so this value will be of decimal number 4. That is, when you consider your decimal number and you convert it into the binary, so the version number will be 0100. So 0100. So 0100 indicates that you are using the version 4. So whenever the sender is going to receive one IP datagram, the first thing he is going to read, first thing is the version. So when they read this 4-bit, now it will be 0100 because we are using IP version 4. Now 0100 indicates that it is version 4. Now if it is version 6, if you are using IP version 6, so then you will be having 0101. So that will be your version 6 value will be having. So this is about the first. The next we talked about the header length or H length. Now this is once again, this is of 4-bit information. So now the length of the IP header. So we know that the entire length of the IP header is of 32 bits. So now which does not include the data bit. So the header value or the IP header, now it indicates the what is the header and from which bits actually the data is going to transmit. So now it is of 20 bytes. The minimum it will be of 20 bytes and maximum it is of 16 bytes. And also we have seen that since it is 4-bit number, so you can start. So when you are saying 4-bit number, it starts with 0000 and maximum you can go up to 1111. So when you say 1111, so when you convert it into decimal, the 1111 is nothing but our 15. but we are telling that the minimum header length is of 20 bytes. So how we are going to get that 20 bytes? Now here we are going to use multiply by 4 method. That means when you read one particular header length, whatever the value you are going to have in that 4 bit, like say for example, so now this header length 4 bit value is say 1010. So if it is 1010, so you convert it into decimal. Now when you convert this into decimal, you are going to get the decimal number is 10. 1010 is 10. Now multiply it with 40, so you are going to get 40. So that means this particular header, that is the length of the header, is 40 bytes, right? This is how it is going to happen. So next we have seen the type of service, that is the 8-bit value. So or it's also called as DSCP, that is differentiated services code point. So it is called as a DSCP or differentiated services code point. Now this is once again an 8-bit. Now if you look into that, already we have seen that the first 3-bit is PPP, so which talks about the precedence or the priority. What do you mean by precedence or the priority? Means this field specify the nature and the priority of our datagram used for routing purpose. Now it plays that what is the priority in which you are going to the packet is there. You can set the priorities, you can set the precedence for each particular packet. Now in the first 3 bits. Now later again we have got another 4, that right? So DTRC. Now D indicates the delay. So D is the delay, T is the throughput, R indicates the reliability, and C indicates the cost. Right? Now when we are saying this precedence, now you can see here there are certain constant values, you can say, like if it is all these 3 values are 0, then it is a normal routine packet what you are having. 001 means priority. So if the value is 010, so it says that to the router that immediately you have to transmit the packet. So like this certain values will be given. So now when you are talking about this delays, right? So in this D, so the first one, see this is a 4-bit number. So you can just see these are the 4-bit numbers. The first D, if it is 1, so if this value is 0 means you don't worry, there is no delay. Now if it is 1, so you don't want to delay that particular packet, so then the value will be 1000. Like say when we are talking about voice over internet protocol or WhatsApp call you are going to make, so you want to see that the packet should not be delayed, because if there is any delay, so you can see the packets are not reaching or the voice is not going to listen properly. So what we want to or the router should come to know that this particular packet should not be delayed in forwarding. So at that case, now this bit will be set to 1, right? So we can see here 1000 means like say minimum delay. So without any delay you are supposed to forward. So after D, the next term is the throughput. Now here if the second bit, if you are going to make it as 1, so that means throughput means the rate of transfer. So if you are making it as 1, so then you are going to allow the maximum throughput, right? So you are going to allow the maximum throughput. The third bit talks about the reliability. So reliability, if you set it as 1, so what it says that we don't want the packet to drop, so there should be a reliable, so we don't want the packets to be dropped, so there should be reliability in the transmitting the packet, so we make it as 1. Now if the last bit, that is the cost, if we make it as 1, so if the last bit, if this bit is 1, right, now it indicates you are going to select the minimum path. So with the minimum path you are going to transmit the packet. So and the last another bit is there, so right now we are not using, this is actually reserved for the future use. Now this is what the we have got DSCP, that is the type of services what we are going to have. Now further, now we have also seen that now we have got in this particular DSCP, now we have got a value or a field called ECN. So if you look into that header packet format, now here again you are going to divide it, and we have got another important 2-bit numbers which is called as the ECN. So ECN, so which is called as explicit right? So ECN means explicit conjunction notification. So we have got explicit conjunction notification. So now this fields, now when you are having, since this is a 2-bit field, now in this 2-bit field, if the value is 1 1, it means that you are going to send a conjunction notification. So before you are going to say only, if you are going to tell that give some notification and inform the router or the receiver that in between there is lot of conjunction, so obviously you are supposed to accept this packet in a very slow manner. So you are going to tell certain conjunction. Now those things have been added. So the next we talked about the total length. So it is of, once again it's of 16-bit. So that means you will be having totally 2 to the power of 16 minus 1, that is 65,535 is the total length packet of your IP datagram, right? Now in this 65,535, if you subtract 20 is the header, right? If you are going to subtract 20 from this, so you are going to get 65,515 is the actual data. This is what it indicates the total length. Now when you go to the next, we have got identification. Now as we already discussed that, now this entire second row, that is identification, we have got bits is of 16-bit, then we have got flag which is of 3-bit, and fragmentation offset. Now this entire 3 bits are used for fragmentation. So why we are using that fragmentation and what it is, now we will be discussing it in our next section, right? So we have identification which of 16-bit, flag is of a 3-bit number, and then we have got fragment offset. We'll come to it later on in shortly. So now we'll go to the next, we'll discuss the next one, which is called as TTL. So which is called as time to live. So as we know that the every datagram packet, so the datagram packet is since it is a datagram, it simply travels in all the path, in whatever path it wants. Now in practice what happens, a router processes the datagram in less than 1 second. A router within 1 second, it is going to, router will forward that particular packet. So now if the packet is not reached to the destination properly, it keeps on rotating. So we have to take care, after certain period of time it should be destroyed. So to do that, now the sender is going to have certain time frame. So how much time this packet should be alive, that is what we call TTL. So every time when a packet jumps from one router to the another router, when it keeps on jumping, or when it is forwarded from one router to the another router, now this field, the value will be decremented by 1, right? And finally if it reaches a value 0, so when the value of this TTL reaches 0, so then whatever the router will do is that now it is not going to forward that packet. It means we are assuming that the packet is been destroyed, so that it does not enters into a closed loop. So the router will going to discard this packet if its time to live period is expired. Clear? This is about our TTL field. So after that we have got protocol number. So now we have got the protocol number, so which is again an 8-bit number. So now what does this protocol number say? That if we are using any higher level protocol in your IP layer, so if you are using some higher level protocols in our IP layer, so now which protocol you are going to use, now that is indicated in this particular field. Like say for example, now some default values are there. So if the protocol value is 0 means it is reserved. If you are having the protocol number 1 means you will be using ICMP, that is Internet Control Message Protocol. If you are using 5, then it is 4 IP encapsulation. 6 means you are using TCP control protocol. 17 UDP you are using, right? Now these certain protocol numbers are been given in that particular field. Next you have got header checksum, which is of 16-bit. So header checksum means, so every time the router, whenever it is receiving any datagram, it checks the header. with the help of the header checksum, it is going to see that whether the header information we have received is correct or wrong. Because so it is just like saying that you write one letter, on top of the letter you write a destination address. If the address itself is wrong, obviously the content is not delivered to whatever required people, right? So first thing you have to see that the destination address is correct, the header address is correct. If the header address is correct, then only a router can forward that particular packet to the corresponding router, so that the packet reaches the destination properly. If header itself is wrong, how to check the header is correct or wrong? So we are going to use this header checksum, right? So if the header checksum does not matches the content, so then it indicates that the datagram is corrupted and it is discarded. Clear? So the next information is the source IP address, which is in 32-bit. So we know that every datagram, since we are using datagram, which is an unreliable mechanism in which the packets are been sending, so we need source IP address as well as the destination IP address. So every datagram should have 32-bit IP address and a 32-bit destination address. So the last option is the option field. So this is a variable length field. Now it can be used for source routing, record routing, and internet time stamp, right? So this, if it is optional, now if we need, we are going to use that particular field. Now otherwise we are not going to use that particular field. So this is what we have discussed in our previous class, that is our IP format. So that is IP packet format, which we have discussed. So next we are coming to another important concept, which is called as the IP fragmentation and reassemble. Now what actually do you mean by the IP fragmentation? So now if you observe this particular diagram, as we have already seen that a host which is connected in a Wi-Fi network, one host, and another host is connected in a point-to-point, right? We have got another network. Now when you have got different types of network and the packet has to go from one different network to another different network via the routers, now the fragmentation becomes very important for us. So what we are telling, what do you mean by a fragmentation? Now actually this fragmentation is done by the router here. Now when an IP datagram, when it is traveling from one host to another, now it has to pass through different physical networks, right? It has to pass through different physical networks. Now you can see here, right? This is, so when this from Wi-Fi, you are connecting to some other network through help of a router. So what is the use of a router? Router connects two different types of network. So in the left hand side we have got, let us assume, a Wi-Fi network. Now here you have got an Ethernet network. Now when you are connecting the two different routers, now it has, the packets has to go through the physical layer. It has to go through the physical layer. Now when we are talking about the physical layer, now each physical network now has a maximum frame size, right? Now each network will be having a maximum frame size. This is what the maximum frame capacity I can have, not more than that, because in my network or in the cables or links what is being used, now we have got certain maximum values will be there. Now that value we call it as maximum transmission unit, or it's called as MTU. So we are having the maximum transmission unit. Now it limits the length of datagram that can be placed on the physical frame. So we can try to limit, like say for example, now let us assume that we have one network here. Now this is our Wi-Fi network, right? So we have got a Wi-Fi network. Now we have another network, let us say this is an Ethernet. So we are having an Ethernet. Now we have an Ethernet here. So in these two different networks, now we are going to connect to each other with the help of a router. So we have a router in between, so we are going to connect. Now when the packets, when you are going, now it depends upon the capacity of this link, because the router has to forward one particular packet here. Now what is the size of the packet here? Now the size of the link here, because this is completely in the Ethernet. So a datagram, now since it can travel throughout different networks, now each router and decapsulate the IP datagram from the frame. So it is going to decapsulate the entire datagram, and now the size what we are going to receive the frame. Now it depends upon the protocol. So using by the underlying, we can say, physical network. So if you assume that the packet what you are going to receive, let us say that it is the size of this packet is 200, or let us say that 2000, but the capacity in which this link is been connected in the Ethernet, is it possible for us to transmit this huge packet via this? If you are not able to transmit, so then we have to divide this packet again. So we are going to fragment this packet again so that it can be transmitted. So this is what it is going to do, the router. So what the router does is that it is going to first see what is the maximum transmission unit. So what is the maximum transmission unit in this network? Based on that, it takes a decision whether can I send this packet directly. If the packet size is less than the maximum transmission unit MTU, you can transmit the packet. If the packet size is more than this, so then we have to do the fragmentation. So to enable the forwarding, so what the datagram in such cases, now what IP does, the IP implements the process to fragment the datagram exceeding the maximum transmission unit. So the process, this particular process, it creates a set of datagram, so within the maximum unit. So a datagram can be forwarded by the source or any router in the path. So fragmentation, generally it is done by the router. Now, and once it does the fragmentation, at the other end, the reassembling of the fragmentation or the reassembling of the datagram can be done. So when a datagram is fragmented, now how we are going to achieve all these things? So as we have seen that, so in our IP format, so we are using three important fields, right? Now if you go to this IP datagram format here, now there are three important fields. So one is the identification bit, the flag bit, and the fragmentation offset. So now these three fields are the main thing for our fragmentation. So in order to do the fragmentation, now we are trying to consider these three bits. So what are those three bits? So one is the identification bit, so we have got the flag bit, and the other one is the offset bit. So now let us understand each one, so what these particular bits are going to do. So these are the three bits. Now you can see, so we have identification bit, which is of 16 bit, then flag, it is of 3 bit, and the fragment offset, which is of 13 bit. So now we divide the datagram into small packets, right? So what we are actually doing, so entire datagram, now let us say that if this is your datagram, all right, this is one packet you want to transmit. Now if you want to transmit this packet, now you are going to check the maximum transmission unit. So you are going to check the maximum transmission unit in this line. So from one network you are going to transfer this to another network. So what router does, it will check what is the maximum transmission unit. Now if the maximum transmission unit is less than the size of this packet, so what router does, it further fragments this packet, right, and it sends it. Now when you are going to fragment this, now we should know, because after doing fragment, now it is a datagram. Now each one is going to move in our network, right? It moves in the network. At the other end, the receiver should come to know, or the another router should come to know, that this packet is, this small fragment belongs to this packet. There might be another datagram, right? So there can be another datagram. Now this datagram can also be fragmented. So now we should know that this fragment and this fragment, right? Now if you consider this fragment, now this fragment belongs to this packet datagram, this fragment belongs to this datagram. How we are going to do? So we are going to identify this with the help of this bit called as identification bit. So to identify all, we are using this particular identification bit, which is of 16 bit. Next comes the flag. So now this is very, very important. Now the flag, it has got again three things. So first is 0, that is reserved. Now it has been reserved. Now you will be having 0 here all the time. It is a fixed, or we can say a constant value we are going to have. So in this flag, most significant bit, the flag bit, the most significant bit, MSB, this value, now it is reserved to 0. Next we will be talking about these two values. Now these are very important. So that is, again, we have still another 2-bit number. So one is called as a DF. Let us say that 0 0. So we can have 0 1 1 0 and 1 1. Since it is a 2-bit, so these are the values you are going to have. So here the first one is called as DF. DF means do not fragment, right? So now this field, now it can be either set to 0. See here, now if you take that this is our DF, let us say this is DF, this heading is DF, and this is MF. MF means more fragment, DF means do not fragment. Now if you consider this as a small table, now DF can be either 0 or it can be 1 1. MF can be either set to 0 or a 1. Now if our do not fragment bit, or that is DF, if it is 0, so what it indicates, there is a fragment. That means if the DF values are 0, now these two values, if it is 0, then it indicates that now this is a fragmented packet, right? It is a fragmented packet, or we need to fragment that packet. Otherwise we cannot transmit that entire datagram. Now if it is set to 1, if you are going to set this field to either 1 1, so you are not going to fragment. That means no need of fragmentation. Fragmentation is not required. Similarly, more fragment. So the next bit is more fragment. So it can be also set to either 0 or 1. Now this more fragment, now it tells that whether the packet is the first fragment or whether it is the last fragment, or is there any packet or there are any fragments which are preceding. So before this, like assume that now we are going to read this bit. Now in front of this, is there how many fragments are there in front of this? So it can be identified, right, by using the more fragment bit. And the last 13 bit is of offset. So what is this offset? It is number of bits ahead of you, right? So it indicates that how many bits are ahead of our particular bit. So these are the three important fields what we are having. So now we will try to take an example and we'll try to see that how actually all these do not fragment, more fragment, identification bit, all these bits, how we are going to use this. Now we are going to take an example and we will be trying to see that. So now if you look into the in your textbook also, now you are going to see this particular diagram here. Now now you can see here, now we have some datagram and the packet size is given. The size of the datagram is 1400, right? Now when this 1400 from router to, when it is going to a point to point where the MTU is very less, so now this 1400 are being divided into fragments. So 512 bits, 512 bits. Now we are going to divide it into smaller fragments and we are going to send. So now for us, our question is that now when you are going to send this, you will be having some identification number, right? Then we have got a flag bit of 3 bit. 3 bit is a flag, right? Now in this, the most significant bit is reserved, so we don't worry about it, it will be 0. The second bit is called as the do not fragment, right? The DM bit is there, then more fragment bit is there. So now this bit can be either set to 0 or 1. Then we have got a offset of 13 bit. After that we have the remaining of our header of our rest of our header, and we have got the length, right? So what is the total length? Now based on this, now the router will check the most maximum transmittable unit, MTU. Based on that, it takes a decision that whether this data, which is 1400, whether I have to divide it. So it has been divided. Now you can see now we have an one fragment whose size is 512 bytes, another is 512 bytes, and remaining will be 376. Now when you add up all this 512, 376, you will come to 1400. Now how we are going to do all those things? So we will try to understand it with a simple example or a problem, right? Now let us take, what is our problem? Now a datagram, we have got a datagram of 3000 bytes. Now what is the size of the datagram? 3000 bytes. Now in this 3000 bytes, 20 bytes is of header. So header takes how many size? 20 bytes is the IP header, and so when you subtract 20 from 3000 bytes, the remaining 2980 byte is of payload, right? Now this is the actual data. What is your actual data in this 300 bytes? 2980 bytes is the data, plus 20 bytes is the header, IP header. Totally the datagram size is 3000 bytes. Now this datagram of 3000 bytes, now it reached at a router. Now a router, it receives one datagram packet. Now what is the size of the packet? Now it is 3000 bytes, and now router must forward this to a link. Now it has to forward it to another link, and it will check the what is the MTU, that is maximum transmission unit on that particular network, right? Now if the maximum transmission unit is 500 bytes, what is given in our problem? It is 500 byte. Now the size of your datagram is 3000 byte, but you can send only 500 bytes in that. So more than 500 bytes, this link is not going to accept at all. It can accept only size of 500 byte. Now you see your datagram size is how much? 3000 byte. Now the router cannot send this packet or datagram in this link. So what the router has to do? Router has to fragment. It has to divide further. Fragmentation means again this datagram which is of 3000 bytes. Now router has to divide it in such a way that now it can be transmitted in this particular link. So how many fragments will be generated? So to transmit this 3000 bytes on this link which has got a MTU of 500 bytes, how many fragments you want to divide? What? And also write the MF, right? What is this MF? More fragment. So you have to write the MF, you have to calculate the offset, and you should write the total length. So this is what the problem says. Now let us try to analyze this particular problem. We will see now how each bit is going to come into the picture. Now what is given for us? Now given for us is the datagram packet. So the packet size is of how much? It is of 3000 bytes, and your maximum transmission unit in this link is just 500 bytes, right? Now router is going to receive a datagram which is of 3000 bytes. You have got a link. Through this link it is connected to another network, right? Now the router has to forward this datagram. So but the maximum transmission unit on this link is just 500 byte. That means you cannot transmit this completely. You cannot transmit this datagram because this datagram size is very huge. It is very simple, right? Input size is more, your channel is very less, it is accepting only 500 bytes. Now out of this 300 bytes of the datagram, now if you observe, 20 is of what? 20 is the header. We know that, we have just seen that IP header size is minimum header size of IP version 4 packet is 20 bytes. So 20 bytes is the header. If the header is 20 bytes, then what is the actual data payload? The payload is 2980. Now first question, how many fragments we have to do? So 3000 we are having, you have to, the MTU is 500 bytes. Now see, now we are going to send this datagram now with on a channel of how many? 500. The capacity is how much? 500 bytes. Now we have to divide this 300 into 500 bytes, right? Because maximum transmission unit is 500 byte. Now we can transmit at a time how many? You can transmit a fragment. The fragment size should be how much? 500 bytes. Now if you are considering the fragment size of 500 byte, you know that even though a small fragment you are going to take, now this is once again transmitted. It is transmitted, and our internet protocol is of what is the way in which the IP is going to work. Now IP is going to work with the datagram. So that means now it is simply, these datagrams are simply going in any directions. So obviously every fragment also needs an header. Now we need a header. So out of 500 bytes, 20 byte will be the header, right? That is the minimum size, and the remaining 480 byte is the payload. This is the data. Now if you are able to transmit 500 bytes, in that 520 bytes should be our header. So actual data, how much you can payload size will be of 480 bytes. So now we want to calculate how many fragments we can do it. So what we are going to now do, how do you do the calculation? So what is the actual data? Out of 3000 bytes, actual data is, actual payload is 2980. So 2980 bytes divided by, what is the actual data you can transmit in your link? 480, because 20 is the header. You just remove that header part. So divided by 480 bytes, and you take the ceiling value, so it will come around to 7. You take the ceiling value around 6 point something you are going to get, you round off, you take the ceiling value and you say that 7. So that means now what we have analyzed right now is that to transmit this 3000 bytes, we have to divide it into 7 fragments. So you have to divide it into 7 parts, 7 fragments we are going to do. So totally 7 fragments you are going to do. Now let us write these 7 fragments. Let us say that now this datagram whose size was 300 bytes, now it should be divided into 7 fragments. Let us call this as P1, P2, P3, P4, P5, P6 and P7. Now the first fragment P1. So what is the maximum size of this fragment P1? It is 500 bytes, right? 500 bytes. So in this 500, 20 is header, 480 is the actual data, that is the payload. So this is total, we got 500. Now this is first fragment, first packet you have divided. Similarly, what is the next packet? Again 20 header plus 480 payload, so total becomes 500. Similarly, the third is 500, fourth is 500, fifth is 500, sixth is 500. Now you see what is going to happen. Now till when you are up to here, now how much you have, how much data you have transmitted? So 480 times 6, right? We have divided into 6 packet. 480 into 6 comes to 2880. This is the 2880 is the actual size. So now what is the actual data you are having out of 3000 bytes? 2980. How much you have divided? How much already you got? 2880. So the remaining is how many? 100 bytes is remaining. So the last packet will consist of how many now? It consists of 100 bytes plus header is 20 bytes. So it becomes 120 bytes. Till here it was 500 bytes. So all the packets 500 bytes, because maximum transmission unit is 500 bytes. So the remaining, the last packet will be having only 100 bytes. So when you make the total 100 byte plus all this, when you make the total of this, that is 500, 500, 500 into 6. So right, so 500 into 6 plus the last one. So now that gives us the total. So the actual data 2880, remaining is 100, payload is 100, so you get 2980. So this is what the 2980 is, the actual payload. Now this is what our total length of our entire fragment what we are having. Clear? This is how the fragmentation is done. Next we are going to find more fragment, right? So now how this MF bit is going to come into the picture, how we are going to mark the MS bit. So if you take the first packet P1, right, you are going to take the first packet. Since this is the first packet, now you know that there are other fragments, right? Totally how many fragments you have done? 7 fragments, right? So that means now here in this MF field, this bit we will write it as 1. So what does this 1 say? That 1 is going to tell us that still more fragment is there. This is not the end. This is not the end of the fragment, because still you are in the first packet here, right? So you go to the next one. So what it indicates, now when you are here, so how many bits you have transmitted? 480 plus 480, right? But actually still you have 2980 bytes you are going to transmit. Till now you are just fragmented into 480 bytes and 480 bytes. So that means P2 here in this field, now you are going to make F as 1 more fragment. That means still there are fragments are there. P3 also more fragments. Now till P6 this MF field will be 1. Now you come to P7. Now when you are at the P7, you know that this is the last fragment. After this, is there any fragment? No, because we have divided it only into 7 fragments. After this P7 you don't have any fragment is not there. So this MF field will be set to 0. It will be set to 0. That means after this you don't have any fragment. This is the last packet. After this you don't have any packet. So this is how the MF field comes into the picture. You are going to write the MF field. So next, offset. So how you are going to get the offset? So what does the offset is going to tell us? Offset fields tells us that before us how many bytes of information is there, because when you are going for reassembling this fragment, right, when you are going to rejoin all this fragment, now offset becomes very important for us. So now, so let us start with the first fragment or packet P1. Now before P1, is there any fragment? Before P1, do you have any fragment? No, because this is the starting packet here. So since we don't have any fragment before P1, now we are going to make the offset is 0. Before P1 no packet, so offset value will be 0. Next come to P2. Now you take this P2. MF field 1 means what? Still further we have packet. This is not the end. Okay. So now before P2, how many datas are there? Right. So before, now here if you are at P2, so before P2, so how many packets are there? 1 packet. Now what is the size of this packet? 480. Payload is 480, right? 20 is the header. You just leave the header. Actual payload we are supposed to interested. Now the payload is 480 bytes. Now you are going to take that 480, you are going to divide it by 8. So we try to divide all this by, to get the offset we are going to divide it by 8. So 480 by 8 you get 60. So 60 is the offset. 60 will be the offset now for this P2. Now you can see here in this diagram, now offset will be written. So when you are dividing it offset, so initially since this is the first packet, offset will be 0. So next packet offset becomes 64. So how this value you are going to get, because with this only reassembling can be done. So that is what we are calculating here. So you take packet P3. Now before P3 how many packets or fragments are there before P3? 2, right? We have 2. One is P1 and P2. 2 means what? 480 plus 480. So we are taking 480 plus 480 divided by 8. You get offset values 120, right? So offset for P1 is 0, for P2 it is 60, for P3 is 120. Similarly offset for P4 it will be 180. So P4 means 480 plus 480 plus 480 divided by 3. Before P4 there are 3 packets. Like this, if you calculate, now for P7 you get offset value as 360, right? Now let us say that if you take this P4, now what is the offset value we got? We have offset value is 360. Now if you multiply this offset value with 8, 360 into 8, so we are going to get 2880. So 2880. That means now what it is going to tell that before this packet, so 2880 fragments have already gone. Now if you just add for this P1, what is the data? It is there for P1 100 bytes. So if you add this 100 to 2880, you get 2980. That means all the packets or the fragmented value has been sent before P7. Right? Now this is how we are going to calculate the offset, or you can say the more fragmented bits. So this is the theory. Just now I have explained clearly. Now you can just go through this particular thing. So this is what now we are having. So in the next class, now we will be trying to understand now what is the IP addresses, right? So how we are going to look into the IP addressing scheme. So before going into the the IP forwarding, so now we are going to look in our next class global addressing. So now we need to globally, uniquely, we want to identify, because when you are sending in one packet or a datagram from one router to another router across the networks, so you have to identify which network I have to transmit. The router has to decide which network I have to transmit. To do that, so now we need IP address. As we already discussed that IP address is required for the routers. So routers to forward, now it needs IP address, right? Now how the addressing scheme we are going to have. So these things we will be discussing and in our next section. Clear? So just go through these things carefully and try to read it from the textbook. Okay, thank you for watching. Thank you.